I'm Andrei Broder. I work for Google, and I decided that this is a great time to talk about deep learning. And since many people believe that deep learning is the answer to everything, maybe deep learning is the new 42. So we assembled a very distinguished panel here to help us understand what deep learning can and cannot do for us. And I will start by asking the panel to introduce themselves, and then we will have a number of questions from me. And in the meantime, you can ask questions yourself. Here is a URL, and the URL will be displayed all the time. So if you ask questions there, then you will see what people are asking, and you will see, you'll have the opportunity to vote up and down. And the questions that will pop up, we'll ask the panel to answer. Unfortunately, we had a lot of technical problems, which means that the URL for that is now a different URL than the one I tweeted a number of hours ago. Sorry for that. Also, I will have to share with you the presenter view, which will be, you'll see also the questions that were asked that we decided to skip. But so be it. And let's see, I think we keep having some technical issues here. But in the meantime, let me ask the panel to start introducing themselves. So let's start from here.
What do you want, just the one sentence intro?
No,
Okay.
a little bit more than that. You can say a little bit more than one sentence, okay, but no more than 3 sentences.
Okay. I am Jitendra Malik. I am a professor at Berkeley. Can you hear? Okay. My research is in computer vision. I used to be a critic of deep learning, and I, in fact, pushed Jeff Hinton to start doing serious experiments which we in computer vision could trust, and he did, in fact, do those. And at this point, I'm a true believer.
I'm Isabelle Guyon. I have contributed to the winter of neural networks and deep learning algorithms by being a co-inventor of support vector machines. I've known actually a full cycle of enthusiasm for neural networks in the 80s, and my thesis was on neural networks. And I've known, the backlash and now the revival, so I can share with you all of these experiences.
Hi, I'm Pedro Domingos. I'm a professor of computer science at the University of Washington and a longtime machine learning researcher and member of the KDD community. I wrote a book called The Master Algorithm that it's an introduction to machine learning for a general audience. I also started doing research in deep learning long before it was popular. We have an approach called sum product networks that will be the prevailing one in the end. I also do a lot of research in types of machine learning that are not, that are not deep learning. So I think this is a great panel to have. And we have a shortage of microphones. Let's see if this one works.
Does it work at the back? Yeah. So my name is Nando de Freitas, and I'm an Oxford University professor, although I spend most of my time at Google DeepMind in London. And my research is on, mostly these days, on deep learning and reinforcement learning.
Hi, I'm Jennifer Neville. I'm a professor at Purdue University. I have a joint appointment between computer science and statistics. And I work on machine learning methods and data mining methods for graphs and large networks. I would have described myself 5 years ago as an opportunistic Bayesian. So now I guess I am an opportunistic deep learner.
Great. So I don't know, do we have more microphones in the back for the audience that we can use for the panel for the time being? Do we have more microphones in the back that maybe we can use? Well, maybe you can detach the microphone so the panel can use the microphones. Okay, so I would like to cut directly to the chase, and ask the panel in turn whether deep learning is the answer to everything, and what is the question that the deep learning is the answer to everything. But before that, let me ask both the panel and the audience a question that was suggested by my colleague Sulin. How many people here were doing deep learning before it was known as deep learning? Let's just see a show of hands. Oh, quite a few. Yes, many of us did neural network and related problems well before it was all the buzz. So one of the things that you can tell us is how the fact that deep learning became so popular and became a buzzword changed your interaction and your field. So let's start maybe from the other way around. So let's start with Jennifer.
Probably not the best person to start with because I work in graphs, and so I think that deep learning took off more in images and then sequences and has just recently come into the graph space. But as I guess I can say why I started using it, of course I saw the success in other areas in complicated structured data of images and sequences, and so of course I wanted to see if I could port some of the same gains into the areas of graphs and apply it to the problems that I work on. I've had students working on deep learning methods and algorithms in my lab for the last 3 years, and it's taken us that long to get to the point where we have something that works at all. So it was very difficult to apply the methods to the heterogeneity of the data that we have. So we have graphs where nodes have hundreds of neighbors or tens of neighbors, and trying to figure out how to put that into the sort of space of deep learning was very difficult. And since our paper is under submission, I won't tell you how we solved the problem yet.
So I guess depending on how you define deep learning, it can go back to a couple hundred years back in time. To when psychologists came up with PCA and so on. But my personal experience, and I'm not talking about neural networks and so on, but in the modern view of what we do in deep learning, really started with the Canadian Institute for Advanced Research, where Jeff Hinton managed to convince them in Canada to sponsor research into understanding how the brain works. And this was incredibly radical at the time. Now everyone sort of is happy to have posters and booths on, upstairs on this. At the time, it was suicide to say you were going to solve intelligence or do research on understanding how the brain works. But kudos to Jeff Hinton. He managed to put this program together. He brought in people from different, he also reached out to a few others like Josh Benjer, Jan LeCun, Andrei, myself, and it was great. For like 10 years we would get together before NIPS and discuss, how Boltzmann machines were gonna take over the world. In 2010, we had a workshop where Jitendra basically gave us the wag of the finger for not showing applications. And by that time, we had already been in some workshops on GPUs. They were just starting to take over. And it was then just a matter of 2 years before deep learning changed speech and changed vision.
So you probably all know that deep learning is actually the third coming of neural networks, right? The first coming was in the 60s, and then they died for 20 years, and then they had the second coming for 10 years, and then Isabelle personally killed them by making, by inventing kernel machines, right? The kernels were actually her idea against Vladimir Vapnik's, objections, correct? So blame her. No, sorry, actually. No, I correct myself, actually. After, the 80s were the decade of neural networks, and that's when NIPS, the Neural Information Processing Systems Conference, started. And then the joke was that in the 90s, it should be called BIPS, because it was all Bayesian information processing systems now. And then Isabelle and Vladimir and others, they brought about the decade of KIPS, Kernel Information Processing Systems. And I remember joking with Joshua Benju at ICML 2009 that, the 2010s were going to be DIPS, the decade of deep information processing systems. And and when I said this, Joshua just started laughing because it seemed such a crazy idea then. We had no idea just what would happen. But the bottom line is, the next decade is going to be the decade of something else. X ips. What is that X going to be, right? And I think, just to list something slightly more substantive for just a second, deep learning is actually an unfortunate term. We may be stuck with it at this point, but it's really, deep learning is a type of neural networks with more than one layer. That's not what's important. What's important is representation learning. That's actually the better term. Representation learning is, I think, the central problem in machine learning. And this is the problem of learning not just to combine the features in some linear way, which is dead boring, but it's actually what, unfortunately, most of machine learning in practice is. It's discovering those features, discovering representations, discovering latent variables, discovering new concepts. This is what humans can do amazingly well that no machine learning algorithm can do yet. So I think representation learning has a great future. We also need to realize that the kind of deep learning that we have today is a tiny speck in the vast field of methods that we could use to do representation learning. So what I would hope to see is a lot more research on the broad spectrum of representation learning and not just the kinds that we have today.
Thank you for these great remarks. I hardly have anything to say anymore, except some anecdotes, maybe. Thank you for giving me credit to kill neural networks in the 90s. It's not quite true, actually.
And anyway, you got probation, right?
Yeah, right. I got probation. So I was, actually shocked of the entire community swagging, from neural networks to kernel methods. And actually, I'm equally shocked by the swagging back to neural networks and deep learning. I think it's overshooting quite a bit, and we need to keep the diversity and a large pool of ideas and keep things alive. I was myself trying to keep neural networks alive during the winter of neural networks. I went into benchmarking. One of my other hats is to organize challenges in machine learning. And I was, in fact, in the evaluation team of the DARPA deep learning program that was just launched before the revival of deep learning. So I also take some pride of having made it possible for deep learning to come back. And in the 80s, in one of the challenges I organized, everybody was trying SVMs or random forests, but the winner was Radford-Neal with the Bayesian neural network. So that already said something, that the people who stuck to it kept making big advances, and I am also a strong believer in neural networks and deep learning. So at this stage, what are the predictions? Is it going to be like a little big balloon that's going to deflate? Or some people have predicted some dramatic changes. Some people have remembered that back in the AI beginnings, there was 1 year, 3,000 people at an AI conference and 800 the next year. So some people were really scared things would happen like that again, a big bubble that will burst. My prediction is that it's not going to happen. I think that we are on good tracks this time because we have a lot of compute power, we have a lot of data, and this is what deep learning algorithms need. They are very data hungry and they need a lot of time to learn. Not necessarily to be utilized, as Nando mentioned during our previous discussions. They can be fast at utilization time, but they still require a lot of pampering for learning. On the other hand, there's a lot of potential because we have more and more data. So we need machines that can absorb all of those data and turn them into features, into representations. And that doesn't mean that there are not still a lot of applications that, on the contrary, have little data. So those need alternative techniques or complementary techniques. So we need the variety. And the last question is, what's going to be next? What's going to be after deep learning? And well, I don't want to, anticipate too much on the future questions of the panel, but explainability and interpretability are going to be the hot next topics probably. And there I'm working with a bunch of colleagues on causal models. I think causal models will play a role in that, and perhaps even classical AI will also make a comeback and play a role here.
Okay, thanks.
So I'm going to comment on, I think, what are the key reasons why deep learning succeeded in this round. I think I'm going to focus on the AlexNet paper of Hinton, Krzyzewski, and Sutskever, because that's the one which had a very, very big impact in the computer vision community. There were earlier successes in speech, but that's the paper which really launched, I think, the field in a big way. I think there were some advances which happened during this, the phase where neural networks were pursued by a small bunch of people funded by the Canadians, willing to pursue things even though they were not popular. So Nando already referred to this phase. And I think there's some ideas which came from there, like the use of half-wave rectification as a nonlinearity and max pooling and things like that. But I think the biggest change actually came from the availability of label data, huge amounts of label data. See, there have always been competitions which involve some amounts of training data and test data and so forth. What the computer vision community did was, starting from the early 2000s, to have this effort at building bigger and bigger data sets. And in my group, we did something early in the 2000s on image segmentation, with thousands of images segmented out by humans. Then Perona and Caltech did what's called Caltech 101, which led ultimately to ImageNet. What was happening at the same time was that Amazon Mechanical Turk came on the scene, and there were images available on the web. So putting these together meant that you could have data sets with 1 million labeled images. So that was one thing which we in the computer vision community consciously did, because we thought that the statistics of natural images can only be captured by having large amounts of labeled data. Independent of us, the GPU crowd came to the scene, and they were operating on different bases. I mean, they were driven by the needs of gamers and so forth. So I think it's really these three things coming together: huge amounts of label data, a few innovations in neural networks. Otherwise, the basic idea of ConNet is the same as in the 1989 paper of LeCun et al. And in fact, an earlier paper from Fukushima with backprop added to that. It's really big data plus some innovations in the learning architectures plus GPUs. Now, looking forward, and now, of course, last 2-3 years, we have seen sort of all the flowering of this, and we have found that the solutions are not just for one problem, but in fact, the solutions apply to many related problems, and this is why in the field of computer vision, we have gone from being total skeptics to true believers. But looking forward, I see that the easy wins are done. Looking forward, you can see that this style of training, which is huge amounts of label data, this is not the way we can continue. This is not, when a child learns the concept of an elephant, it does not require 10,000 labeled examples of elephants. Okay, your mother probably has to give one example of an elephant. Now, in the old days, the neural network people were onto this, and they obviously talked about unsupervised learning as important. But unsupervised learning never had the same kind of big successes that we have had with supervised learning. Going forward, I think we will have to confront all these other variations of learning besides the classical supervised learning variation. And my belief on this is that we're going to be driven by a lot of insights into how child development takes place, how we know a fair amount now about the various stages in evolution, various stages in the development of a child. The early stage where you have a sensory motor interactions, followed by language, followed by systematic pedagogy and so forth. I mean, this is not the time to go into all the details of that. But I believe that a lot of insights from that will come into play into how we design our systems. There are many, many different aspects of intelligence, and what deep learning has been used for is essentially function approximation in a certain setting. And this is great. This is very powerful. But this is just a small component of what intelligence is about.
Okay, thank you. So let me do a follow-up question coming from the audience. It was a question posed by Justin Ormond. And something I forgot to tell you all is that actually if I pick your questions, then actually you get a prize, namely a beautiful T-shirt courtesy of Google that shows you a brain. So please feel free and please vote for the people that should get a T-shirt. I mean the people
But the best part is the back of the T-shirt that says, "My other brain is a data center."
Yes. Quickly, everyone gets really one sentence. Where will traditional ML continue to beat deep learning? So let's go from Jennifer.
Okay, I think that there's always been a trade-off in machine learning between very complex, flexible models that don't give interpretable results but really maximize accuracy a lot versus simpler models that may be more biased and you get slightly less accuracy, but they're much more interpretable and easy to understand why the model's making particular decisions. I think right now deep learning is in that space of being a very opaque model that's hard to understand why it's making the decisions that it's making. So that's my answer.
Okay.
And that was a very eloquent answer from Nando. Right? You can read a lot into silence, right? If you think of the question. So here's my answer. And here's something that I think we should all remember in these days of deep learning hype. When you look at Kaggle competitions, and when you look at the most recent large-scale machine learning studies, the winners in most categories are not deep learning. Deep learning really dominates in vision, as Jitendra was mentioning. In fact, I've never seen a field swept more suddenly and more thoroughly than how computer vision was swept by, by ConvNets. It's hard to find a paper in CVPR that doesn't have a ConvNet in now, but that's vision. So in vision, definitely ConvNets have swept the field. In sequence data, things like language, speech, and whatnot, deep learning sometimes wins, sometimes doesn't. It's more of a mixed bag. So sometimes an LSTM is the best system, sometimes it's not. But in other fields, in what you might think of as generic machine learning, I need to build a classifier to predict X. The top two approaches there are tree ensembles and support vector machines. And some people these days just tend to apply deep learning to everything, and this is actually very dangerous because deep learning is very hard to use compared to some of these other things. So, if you want the extra accuracy and, for the extra accuracy, maybe deep learning is something that you want to try, but for a lot of things, you still want to use these other methods. They may not be today's latest, greatest thing, but for many applications, they're still what you want to use.
So just to add a little bit to this, I would like to mention the fact that not every data is big, and small data remains very important, or I should say data that have few samples compared to the number of features or variables. And that happens particularly in the medical domain, and in general in many domains in which samples are very costly to collect. And in that case, it's not always possible to get enough data to train deep learning algorithms. Although I should say that even in computer vision, sometimes you have a few samples, but then in that case, you can benefit from networks that have been trained on very large data sets and only retrain the last layer. So I expect that over the next few years, there will be more and more kind of generic libraries of networks that have been trained on lots of data and that you can reuse and fine-tune on new data sets. So, but as I said before, it would be nice to keep alive a variety of techniques so that we can address better and better a wider variety of problems.
Yeah, I mean, just going by the history of the field, it would be wise not to put all your eggs in one basket, right? Because if you went by what was popular in 2000, you would have completely killed research in neural networks. I mean, it is very important for the health of a field to have intellectual diversity. And some people have to be contrarians and pursue something even though it's not the popular approach or not the best yield, not the approach that yields the best results. This is essential for the health of a field. It is important that we have an empirical basis so that we can compare different approaches. And I would expect that over time we'll be mixing and matching in various ways. The ideas that are around are not in opposition to each other. Neural networks is like a building block. It's just like, I just think of it as a function approximation approach. What we've learned is, given lots and lots of xi, yi's, and architecture, a multi-layer architecture, somehow magically we are able to train it with stochastic gradient descent. Different people are able to do it in their labs, and it's somewhat reproducible in terms of the error rates. This is an amazing result, which is empirical in nature. We don't know why it is true, but it seems to be true. But this is going to be just one component.
There was a lot more than one sentence. Okay, so actually, but Jitendra said something which is actually, it's a good lead into the next question, which is there a preference cascade around deep learning? Because deep learning is hot and it wins competition, agreed, mostly in vision, but they certainly, the results are very visible, to make a bad pun. Then the industry makes big bets. Every big industry goes and builds infrastructure for deep learning, and of course the industry builds specialized chips and so on and so forth. So the demand for deep learning PhD goes through the roof, which is, I guess, good if you are into deep learning. And then the research agendas, the money follows that, and you know, there are more wins, and the companies increase the bet, and alternatives are maybe neglected. So do you think that this is happening, and do you think that if you are not a machine learning, you know, not exactly in the midst of deep learning, is there a problem for you? Because it's hard to get funding, it's hard to get students, and so on and so forth. So let's start from, maybe let's start from him. Okay, let's start from Nando.
So the reality of it is that if you have a PhD and you like deep learning, please email me and we'll get you a job. We're desperate. We are desperate to get people with enough deep learning skills.
I'm emailing you.
Okay, so Nando is part of the preference cascade. Okay. Okay, so let's hear from Pedro. Okay, you are part of the cascade.
But actually, I wanted to add something to, I think I really like how Jitendra put how neural networks came up to be and the challenges ahead, and why we take this view that we need more people doing this kind of thing. In addition to the data revolution, the computing revolution, there was also the software revolution. Deep learning these days is not just like a ConvNet or an LSTM or sort of a linear tree-type structure, but they're very modular systems. They're arbitrary graphs that have access to memory, that can attend to, and they can do a huge range of things. They're embedded in decision systems. So of course, deep learning is not everything, because at the end of the day, if you're doing decisions, you might want to keep doing work on reinforcement learning. So it's a good thing that a very small community of machine learning also did not abandon reinforcement learning. That field was almost dying, and then it came back, just like deep learning did. And in fact, that's where we place our bet at Google DeepMind and reinforcement learning. And we've won competition, not just in vision. We've won by using reinforcement, a combination of reinforcement learning, classical search, distilling search into deep nets, and so on. We won the big Go match that most of you saw. So as we go forward, of course, there's also other aspects to learning, like one-shot learning, zero-shot learning, multi-agent learning. That's going to be huge. You're going to have now these networks interacting with each other. They're going to have to communicate, solve problems. So this is going to continue growing. Deep learning really is about modules. There's lots of modules, and people just write their modules, or they compose new modules with existing modules. They submit those modules back to the web, and other people can download it. So the sort of thing that you are pointing out is already happening. There's the rate at which things get produced in GitHub is unbelievable. And it's just because we now have systems to do deep learning that are unlike anything that's written on any book on machine learning. Every book on machine learning at present is outdated. That's not where you're going to learn about neural networks, because they don't see this, the software revolution that's been happening over the last 3 years. Tools like Torch, TensorFlow, Caffe from Berkeley, they've really changed the game. They really have freed people. And then the new thing that where we're scaling besides data and computation and software is people. There are so many people doing this. So like 3,000 people also attending a ConvNet's workshop in Vision. So just I think by sheer magnitude of numbers, and given the flexibility of the approach, given the fact that we can take nearest neighbors, all these traditional techniques in machine learning, we can create modules out of them, and we can throw them into the neural net libraries.
So ultimately, a hybrid approach was going to win. Okay?
So there is no doubt that there's a preference cascade. The question is, what should we do with it? Let me start by saying something that maybe is obvious at this point, which is deep learning is real progress. Right? I know there's people in machine learning, for example, I know a lot of Bayesians who can't stand deep learning. They just hate the guts of deep learning and can't wait for it to go away. And it's not going to go away because it is real progress. Like the improvements in things like object recognition and speech recognition are spectacular, and that's what led to this wave of hype. Having said that, there is a wave of hype. Some of that wave of hype is fed by industry. Some of that is, because, companies want to grow and they want the next big thing and so on. Some of it is the media, but it's there. And in fact, I would say that at this point, it has actually reached dangerous levels in the sense that, one, it's creating expectations that can't be met. And number two, it's creating a very distorted picture of reality. If you think about it, there's computer science and there's a subfield that's AI, there's a subfield that's machine learning, there's a subfield that's neural networks, and there's a subfield of that's deep learning. And now deep learning has become so prominent that people mistake neural networks for deep learning, and now increasingly they mistake machine learning for deep learning. And lately they actually started to mistake all of AI for deep learning. So probably one of these days they're going to mistake computer science for deep learning, right? Everything is just deep learning. And then maybe one day science and technology will be abolished and they'll just be deep learning. Now, this is obviously not a path that we want to go down, right? So now the question is what do we do about it? I think what we need to do is two things, right? We need to keep trying to set the expectations correctly and make sure that people understand what can and what cannot and what maybe can be done with deep learning. But the other thing that we need to do is we need to try to steer this in a useful direction. I remember when I came to the very first KDD in 1995. Back then, there was this wave of hype about data mining, right? Data mining was the next big thing, right? People think that machine learning is like this thing that exploded in the last 5 years, but actually there have been previous such things. And I remember a lot of people saying like, oh, this is just a wave of hype. We should just like ignore it or clamp down on it or whatever. But my point of view then, and I think it's been vindicated in the 20 years since, is that data mining wasn't just machine learning or just databases or just statistics. It was a whole new set, it was a combination of those things. It was, taking both computational and statistical and human concerns into account. So in the same way, and now we have this great community where these things have been married and has made enormous contributions already. So I think we need to do something similar with deep learning, is try to steer it in the direction of what really are the important questions. And we also need, like for example, representation learning, which I mentioned before. And we also need to realize that, we are, even within deep learning, we are still in a very, very primitive state. Deep learning, as it exists today, is extraordinarily inefficient in data, in computing, and in people. Deep learning algorithms, again, they're no different from the rest of machine learning in this respect. They don't generalize very far from a data point. There's all these great examples of how they fail as you go even a little bit far. So the result is that to approximate any function well, you need a huge amount of data. So it's very data inefficient. We humans are much better. It's also very compute inefficient because gradient descent is an intrinsically inefficient way to learn because it updates things very little at each step. And maybe worst of all, it's very inefficient in the use of the most precious resource of all, which is us. Deep learning is an incredibly inefficient use of data scientists. You have to spend all that time tweaking things and finding the right architecture and whatnot. One data scientist 10 years from now should be able to do 100 or 1,000 times what he or she can do now. And those are the problems that I think we should be focusing on.
I think I'll give it to
Okay.
Jitendra.
Sounds good.
I
Go
think
ahead.
I'm at a loss for words.
Okay, so, all right. Oh, Jennifer, sorry.
Okay, so what I would say with respect to this question is that we should use the hype to our advantage to get more money, more funding, more resources. But I would encourage you all out there who are going to start working on deep learning to focus on not the engineering that Pedro was talking about doing manual search over parameters and structures to try to get the best results, but instead focus on getting to the scientific understanding of why the methods are working well. Because Nando might disagree with me, but I would say that the current successes in deep learning are standing on the shoulders of the scientific understanding that we have achieved in other aspects of machine learning about how to create representations, how to formulate a problem as a search problem, how to do optimization in that space, and when it's too complex, how to make smart decisions about how to heuristically initialize and put bias over how we would search over that space. So if, as you go forward and do your deep learning, which I know you all will, I encourage you to just focus on those larger questions, because then the scientific findings that we achieve from this phase will fuel the next phase and the next model and the next representation that we come up with.
Okay, thank you. So let me switch gear a little bit and discuss also some of the costs of deep learning. So one thing I wanted to share is this diagram, which is from a recent report called Rebooting the IT Revolution, a call to action, and it's done by the Semiconductor Industry Association and Semiconductor Research Corporation. And one of their main points there was that if you take today's world energy production and you look at the amount of computing that's being done, and you simply extrapolate at the same rate of growth. And then you look at how much energy is needed simply to change a bit from 0 to 1. So that's the only thing they are really using for the amount of energy. So with today's technology, we'll use up all of today's energy by 2040, which is not that far away. Of course, as some of you might know, there were papers at the beginning of the century that were showing that New York transportation will be impossible because the amount of horse manure on the street will grow so much that horses will not be able to clean it up. So you'll need, the system will become unstable. Well, in the meantime, a little invention changed the dynamics. So what they show, though, that invention is not going to be silicon, that even if you take the limit of what they think it's possible to do in silicon, which is about 1,000 times less energy, so you will just need about 10 to minus 17 joules per bit to change the bit, you're still going to run out of today's level of energy. And even if you go all the way to Landauer's limit, which is a physical limit believed by most physicists that's necessary for deterministic systems, we will be in trouble. So the question here is, will eventually the model size, consumption of energy, and all those things essentially limit the development of deep learning? Or you expect that algorithms invention or development in technology will take care of that? But the point here is that maybe hardware will not come to the rescue as hardware came to the rescue of many other slow things that we try to do in computer science. So where shall we start? You want to start? Okay, Jitendra.
I think I'm not an expert at the hardware level, but just an obvious remark the GPU way of doing computation, so using vision as an example, is so different, so much more energy intensive than the way computation happens in the brain. The brain consumes much, much less energy, otherwise we would all be fried. And there would be no, so clearly there is room for lots and lots of algorithmic innovations. In particular, the kind of we may be able to manage with far fewer bits with much more approximate computations. And how to do that is an interesting question. This has been talked about for decades, and it has always failed in the past. I mean, Carver Mead was trying to build these neuromorphic chips in the 1990s and didn't go anywhere. And there have been periodic attempts, and there are current ones which I will not name. But at some point, it will be that one of these ideas will succeed, because there is no inductive theorem here. It's not that because it has failed in the past, it is guaranteed to fail in the future. I treat that as an optimistic statement.
So I'm a fatalist. I think that people are wasteful, and they will be using whatever is available and waste resources eventually. So I have an anecdote to tell about when we were working on handwriting recognition back in the 80s, 90s. Everybody thought that we would be replacing the keyboard very shortly by handwriting, and that tablet computers that are now very popular would just be using the pen, and this didn't really happen. But at the time, there was a company who was making pretty good cursive handwriting recognition that got bought by Apple to make one of the first so-called personal digital assistant. The ancestor of the iPhone was called the Apple Newton. And that company was from Russia. And the reason why they could fit on a small handheld computer that was not that powerful at that time an entire handwriting recognizer was that they actually were from Russia, and back in Russia they had very non-powerful PCs that they had to program very, very carefully and very, very efficiently. So I think, you know, whatever people have available, they will use it, but we can make our algorithms much, much more efficient.
Energy consumption is the limiting factor for AI today, and for computing in general. Your brain uses about 20 watts, which is less than most light bulbs. So in fact, if somebody calls you a dim bulb, that's a compliment. That means you're very energy efficient. If you contrast that, so that's extraordinarily energy efficient. Contrast that with one of the latest neuromorphic chips out of IBM. And if you had, somebody did this estimate, if you wanted to build a brain of the same computing power as the human brain out of such chips, you know what the energy consumption of them would be? It would be bigger than the energy consumption of New York and San Francisco put together for one brain. So this is just mind-bogglingly bad. Now, what's interesting is that for the first 50 years, we actually did not have the computing power in AI to compete with the human brain. Right? Your brain is the greatest supercomputer on Earth. But we are actually now at the point where, give or take, and depending on how you consider it, we actually have comparable amounts of computing power. So that actually, there's no excuse anymore, right? So on the one hand, it's now up to us to figure out what are the, what's the software, what the algorithms to do with that. But also the thing that's going to hold us back is the energy consumption. Another question is so what do we do about it, right? You can imagine dealing with that in silicon, and I think in the beginning that's what's going to happen. And I do think neuromorphic computing, Carver Mead style, does have a future. This is actually it's not even just implementing, neurons in digital VLSI, which would take out a lot of, levels of inefficiency. It's actually having a single semiconductor device that behaves like a neuron, and where you can actually store charge, for example, for the weights and vary it and whatnot. And there is progress being made here, and I think, this is orders of magnitude improvement. But it's not enough to get us to the human brain. The human brain is still much more efficient than that. There's a basic problem with doing things in silicon, which is the connectivity is very low, right? A neuron and the transistor in some ways are similar. They have a similar transfer curve and whatnot. But the neuron switches 1,000,000 times slower than a transistor. So The silicon has a huge advantage there. On the other hand, a neuron has on average 1,000 to 10,000 connections to other neurons, which is orders of magnitude more than a transistor does. The way we are able to achieve parity is that we multiplex. We have one line serving thousands or millions of different connections. But the problem with this is that multiplexing means switching. And switching, as Andrei was saying, means power consumption. So the whole way that we are matching the performance of the brain right now has high power consumption embedded in it. So eventually this isn't going to work. We're going to need different computing paradigms. I don't know if it's quantum computing or optic computing or DNA computing or who knows, right? But I think we definitely need to do a lot of research in that direction. And the other thing that we need to do, again, going back to what Andrei said, is we don't need deterministic computation. We can take the voltages and the integration down to the point where we're almost dealing with individual atoms, and then the noise level will be very high. But for applications like machine learning and vision and speech and whatnot, a high noise level is not a killer. So we're going to have to learn to do approximate computing, and some of that is already happening.
Okay, thank you very much. So let me go to a next question, which also resonates with one of the question asked by an anonymous person, which says, okay, come on, okay. Sorry, this works much better with better technology. Besides solving problems, could deep learning give insights on causality and interpretability? This is a question that I also thought about, but nevertheless, the anonymous person gets a T-shirt, just show afterwards, and I'll believe you. Maybe using some deep network to figure out if you're lying or not. Is there a lack of explainability good or bad? And most people will say it's bad, but there might be some advantages, and I like to point out to some frame around that. So one notion in economics that's been around for a while is the notion of repugnant markets, which are markets that are prohibited for moral concerns. So for instance, surrogate pregnancy cannot be paid. It can be only volunteer in some countries. Human organs cannot be bought and sold. Prostitution, again, in some countries. Vote buying, I guess everywhere is not legal because they're done very often. Horse meat for human consumption is illegal in California, but of course legal in most countries in Europe. So now, this is a term I haven't heard, but maybe I'm making it up. Is there such a thing as repugnant data or repugnant machine learning? So for instance, genetic data, except the presence or absence of a Y chromosome, is not legal to use for life insurance. So it's a data that also very predictive, we cannot use, and there are many other for health insurance, pre-existing conditions cannot be used. For credit, redlining or zip codes or things which are equivalent with redlining cannot be used, and so on. In fact, this is a very interesting subject, and there is a series of workshops that some of you might be aware called FAT, Fairness, Accountability, and Transparency in Machine Learning. This is now, I think, in the third year. There will be a soon one in New York. And, oops. And this has also now become a big part of the public discussion. Very recently, ProPublica published an article called Machine Bias, where they claim they identify a bias in a system called Compass, which is a system used for predicting risk of reoffending. And therefore has a role in sentencing. As it turned out, that article is actually wrong, but that's not important. It got a lot of buzz around it. On the other hand, there is a solid article by Jennifer Skim and others about gender risk assessment and sanctioning, the cost of treating women like men, where she makes the point that because we are reluctant to use gender as a variable in the model, as a result, actually, the system, the risk assessment for women in sentencing is overestimated. So those are obviously very important questions with a lot of social impact. So I'd like to ask the panel, what are your opinions about this entire controversy, and what is the role of machine learning here? And is deep learning better than some systems which are more explicit, or is actually even worse than the system where the variables are maybe more explicit than in machine learning? And one other thing is that many people use explainability and interpretability interchangeably. Many people think they are very different, so please comment on that as well. So where shall we start? Okay, we start from.
I'll start because I know that the other ones are going to make very, pointy comments on that. I think you have actually many questions in
so
your
feel free to answer only a few. Don't answer them all.
it may be puzzling to the audience actually what the relationship between the various aspects of your questions are. And I see at least one relationship which is important between the quality of data, bias in data, and causality. So those of you who have been attending yesterday the causality workshop may already be a little bit familiar with this difference between observational data and experimental data. So a lot of the data that we are dealing with in machine learning and in deep learning is observational data. So the data that you can just collect freely, download from the internet, etc. And those data are sometimes plagued with so-called sample bias. So typically, you have been collecting data about, say, hormone replacement therapy, and you see that there is a correlation between women who've been taking hormone replacement therapy and heart disease. So this is an actual study that has been conducted, and contrarily to a common belief that hormone replacement therapy increases the risk of heart disease, that study, based on merely observational data, found a negative correlation. So that triggered actually a clinical trial where there were some experiments in a very controlled study, this time with a sampled population with control patients and patients that have been given the treatment. And then the conclusion was opposite. So I think one of the aspects of what Andrei is covering is very important, and that is not only what variables you put into your system, but also how you sample your data, and whether your data came from some just observations or whether there were some controlled experiments performed in order to train your model. So this is where there is this link between causality and the data you put in. Now there's this whole can of worm that gets open here, and this whole controversy about whether given the fact that bad uses can be made with data, particularly with data that haven't been collected in a controlled manner, should we forbid the use of some data? Should we encourage people to use more and better data? Should government have some policy about which data can be used or not, and whether there should be commissions to control whether the data that go into your model have been properly collected or handled? Given the fact that you cannot blame deep learning or machine learning in general for giving bad answers if you give bad data at the input. So I'm now opening this up to other people.
Yes, let's keep.
So I think Andrei asked really two main questions. One is this issue of interpretability and explainability, and another is this question of repugnant machine learning. So let's look at each of those.
Let me explain how I think that the two are somewhat related. Because
they are indeed related. So and let's also see what the connection is. On the first issue, you may be interested to know that the European Union just outlawed deep learning. If you are a company doing business in Europe, when this law goes into effect, you will not legally be allowed to use deep learning. Why is that? Because the European Union just passed a law that says every algorithm that makes decisions of consequence has to be able to explain why it made that decision. Right? Sorry? Well, actually, part of why I think it was a mistake, but part of why they exited was these regulations, right? The European Union has this habit of, regulating first and asking questions later, as with the right to be forgotten, and data can only be used for the purpose that it was collected for. Each of these things is stupider than the previous one, and the latest one is the best one yet. Now, what is the issue here, right? Is that, of course, an algorithm being able to explain its reasoning is extremely important and desirable. If an algorithm tells me I have lung cancer and I need surgery, I would like the algorithm to say why. So I think we can all agree that this is desirable. But here's the thing. As Jen was mentioning, there is a trade-off between accuracy and explainability. Should I use the algorithm that explains itself better or the one that's more accurate? Actually, I want the more accurate one. If I know that the algorithm is more accurate, I don't want to die of cancer, and I don't want to go through unnecessary surgery. So why should anybody be writing regulations that forbid the trade-off from being made by the user? Unfortunately, this is a microcosm of what's about to happen with machine learning more generally, which is governments putting in place regulations that are based on misunderstandings of machine learning that wind up being extremely harmful, often to the very people who they are trying to protect. There's this whole sea of nonsense being written today about how biased machine learning algorithms are and how we need to rein them in. The ProPublica is one example, but an even simple like that. Here's an even simpler one: predictive policing. Right? This is using machine learning to send police officers to the places where they are most needed. And a lot of people say that this is biased because it sends them into minority communities, so it must be biased against minorities. Well, what is biased against them is to send the police officers to where they're not needed. So people need to understand, right, what machine learning algorithms really do and what is biased and not biased. Every example that I've seen of supposed machine learning biases isn't. Like the ProPublica paper, they botched their statistical analysis. There's these things which you've probably seen about, like, oh, Google shows more ads for high-paying jobs to men than to women, so it's biased against women. Well, why? It probably has very different reasons. Like, for example, women may have, like higher value goods that they want to purchase. There's all sorts of reasons why that might be happening. Or like, like Google Images labeled, this is an even more famous one, labeled an image of black men as gorillas. Now, this is shocking, but we have to understand that the learning algorithm isn't biased, it's just stupid. These are totally different things. A learning algorithm that can, these are deep networks at work, right? Deep networks can mistake an ostrich for a car. Mistaking a human being for a gorilla is a much smaller mistake than that. It's just a much more sensitive one. So this is what the learning algorithms need to know what the utility function of the user is. But what we're seeing right now is saying like, oh, you cannot use these variables because they're correlated with race or gender. Well, if you can't use variables that are correlated with race or gender, you can't use anything. I strongly believe that the job of the machine learning algorithms is to make the most accurate possible predictions. It's decision theory. There's the probabilities and there's the utilities. The job of the machine learning is to produce the most accurate probabilities. What we see happening today is people proposing ways to manipulate the learning algorithm to make reality look like what they want it to be. This is wrong. The learning algorithm, for example, to make things more even by race or gender or various things like that. The job of the learning algorithm is to be as accurate as possible. But the learning algorithm does not make the final decision, we do. The utilities are ours. We can decide as a society, as human beings, what our utilities are. And then the decisions are a function of the utilities and the probabilities, but we should not mix up the two.
Okay.
So there was a technical aspect to the question, which was causality first. Causality and deep learning are orthogonal things, and they can go hand in hand. So for example, when we do deep reinforcement learning, those systems are interventional, and just by that nature, they are systems that can uncover causality in their environments. So our agents are already discovering causal effects. Also at the level of observational data, the methods that were used, the mathematics behind, say, least squares temporal differences are precisely identical to the mathematics behind methods to do causality from observational data. So methods like instrumental variables or errors in variables. And in fact, if you go back to the original papers of Bradka and Sutton and so on, you'll find out that they derived a lot of their algorithms using instrumental variables, which are the tools that a lot of folks in causality studies use. In terms of explanation, there's also been a lot of work in deep learning in trying to make the networks more explainable. There was a very nice paper by Carlos Kessler recently, and there's really been many other papers. Ultimately, we would like to have neural networks spitting out in natural language a explanation of why they've made the decision that they've made. This is still a research question, and it's a very difficult one because this network could deceive you, depending on how we train it. So this is a huge challenge that we're facing into the future. And that takes us into the second part of the question, which is the ethics of it. Machine learning, and I always teach this in the first lecture every time I teach it, it's an inductive science, and there's no right to answer when you do machine learning, right? You know, you put a bunch of points on the plot, you pass the students to the board, they each fit the curve through those points, and all those curves look different. People tend to like some inductive biases like continuity, smoothness, maybe recursion, and so on. But fundamentally, it's an ill-posed problem. So we have to make sure that we inform the public that what our models are fallible. Our cost functions for evaluating performance are fallible. We discussed them at length in conferences. We were having this discussion early on, in fact. Quite often we find out after 5 years of research, whoops, this is not the best measure to understand what the method is doing, or you realize there was a mistake. You could have methods that are interpretable, like decision trees. So like NHS in England likes to use decision trees. But if your data is non-IID, if you're breaking the assumptions of how you fit the decision tree to your data, then yeah, you get something that's interpretable, but it's bogus. It means it's not really useful. So ultimately, what we want to do is, to me, there's only two answers to this. Education. We need to educate people better. Education right now is terrible on our planet. It's not fully democratized. It's a huge problem that we need to keep on working on, because it's only until kids in high school understand Bayes' rule and understand like sort of fundamentals of inference and conditional probability and so on that we will expect them to make the right inferences and the right conditioning and the right decisions. The other thing is, I always feel it's kind of arrogant to talk about how to solve the world's problems from this perspective, where our field itself is so non-diverse. So to me, if we're going to be talking about diversity and how to make the world better and so on, we need to diversify ourselves. First, the number of black people here is extremely unrepresentative of the number of black people in the entire world. That is a problem. It's not to blame anyone, but we need to be aware of it, and we need to be thinking of constructive ways on how we stop that from being the case. Same with gender, same with wealth, same with many other things. So it's only when until we ourselves become representative that I think we will be able to actually attack these challenges responsibly.
Okay. Jitendra? Okay, anyone else?
I'll add something to that. Thanks for reminding me. So I guess I would say I agree with what's been said, but we spend a lot of time working on how to develop a new model and an algorithm to learn that model. And then we often punt and say things like Pedro said, like once we've learned the model, it's up to the policymakers to assess the utilities and figure out how to apply the decisions from those models. But there is a place in between there for research to be done on the methodology of how to understand, how to evaluate our models, how to make decisions or predictions about how and where they will apply. And if you want to work on a very non-sexy area of machine learning and data mining, work on methodology, because nobody really cares about sampling methods and deciding what's the right population and how to decide if the distribution we've learned is not quite the distribution that we're going to apply it to. And all of these kinds of questions really come into play when we start rolling out the models and making decisions about them. And I think that we as a community like to say, well, the model's just learning from the data that we give it, right? So if you don't like what the model is saying, give us better data, and then sort of push that problem off to other people. But we need to be the ones to say, this is the sensitivity of our model, our algorithms, to the data that you give us. And here are the very important data points that, that the decisions that the model is making are depending on. And if those are wrong or don't make sense to you, then go get better data. So I encourage you all to work on the next big area of methodology.
Okay.
Just to be clear, I'm not advocating, pushing methodology off to other people. Quite the contrary. If our job is to produce the most accurate possible models, all of these things are important parts of it. How good is the data? Can we make it better? What are the assumptions that we're making? Can we make them better? How do we assess? How do we evaluate?
Yeah,
so all these things, I think, we're actually in complete agreement.
Not right now, I think we. So we'll take a question from the floor in a second. You can put question in the meantime online, and we'll answer some of the online questions. So, okay, any more comments? I mean, this is obviously a very controversial area, and probably we could have had a panel just about that, and not something that we're likely to resolve. But I hope everyone got an introduction to that. And there is a lot more to read, and as I said, there is a series of workshops that are really intended to that. So let me do one last question for the panel, and then we'll do some question from the floor, and we'll do some of the question that were posed online at the URL. So the last generic question is, if you have a new bright PhD candidate that comes to you for advice, and what he or she asks is that, should I go into deep learning, and compete with 5,000 other smart students, or shall I actually do something more in a different branch of machine learning, where maybe it's not so much in the limelight, but maybe there are more interesting things to do and more unexplored territory, rather than simply train a model over another set of data that no one has. So, Jitendra, what do you say?
Okay. Well, I do get these people every day, so my generic advice is, first of all, never be narrow. I mean, I've been in my field for writing papers for more than 30 years. And over this time, I've seen 2 rounds of neural networks, a phase of support vector machines, random forests, many other things in between. Things come and go, and over the course of a 30-year, 40-year scientific career, you're going to encounter many transitions. So you have to have broad knowledge. You must know the fundamentals. You must know basic statistics. You must know about bias and variance and these kinds of very important fundamental ideas which sort of provide the broad context in which specific approaches are developed. Obviously, the approach de jour is very useful, because very likely this is the path of gradient descent. This is what's going to lead you to more success. Finally, as a vision person, I want to say that the techniques, various kinds of learning techniques or deep learning techniques, is only one part of the answer. The other part of the answer is the problems to which you apply these two. And in our business, I believe that a lot of time, good techniques are developed in response to good challenges. You don't do machine learning work in the abstract. In fact, statisticians don't do work in the abstract. Fisher used to work on evolution and genetics. I mean, the great Fisher who invented maximum likelihood. So in our field, I mean, obviously AI provides a lot of applications, vision, speech, language, symbolic reasoning, robotics. I mean, robotics is an example where current techniques have not made much headway because you really don't have that same kind of large amounts of label data. And doing experiments of the time that you can do in reinforcement learning can't be done easily because it's a real robot, so you don't have the ability to do millions of simulations. So I think working on problem domains is a good way to keep you grounded, and many ideas will spring from that. So my one summary is, if you want to understand and contribute to deep learning, know more than just deep learning.
So when I started doing research, one of my mentors said that there are two types of people, and you need to know to which type of people you belong. The people who like skiers, like going on groomed slopes and go very fast, and the people who like going to ski in the wild and enjoy, the deep snow. So if you are a groomed slope skier, then you have a lot of competition, you need to go real fast, and then if you are a deep snow skier, you have a less competition, but you have much higher chances of falling into a hole. So here is, your choice here in research. I encourage very much people to learn and know as much as possible a wide variety of algorithms, not let themselves, necessarily be swept by an enormous tsunami. But on the other hand, you have to know which kind of researcher you are. I'm a slow person, so I tend to be more a deep snow person. So if you are more like the deep snow kind of person and want to go for a PhD, please contact me. I very much like venturing in areas where there are very few people. So even though, it might be surprising to you, but when I started on neural networks, there were very few people that were working on neural networks. The whole conferences on neural networks were maybe like 30 people at the time. And after that, when I started working on support vector machine, the kind of conferences we were going to, like the computational learning theory conference, was again like 30 people. So, and it changed over time. So don't be afraid to go to small conferences where there are only 30 people, because they might be the next deep learning, who knows. At the moment, if you ask me my pronostics, I think causality will be a big next hit. And people interested in working in causality, please, follow me. And then to conclude that, I think that you have to work in what makes you feel enthusiastic and gives you energy. And I would like to cite also one of my mentors, Vladimir Vapnik, who said, don't do cheap research.
When a student asks me, should I work on deep learning or some other area of machine learning, my answer is yes. Because you can do great research in deep learning and you can do great research in other areas of machine learning. So in some ways, that's not the important question. The important question is, what is the problem that you really care about and how are you going to solve it? And you should solve it with absolutely no preconceptions. What you should absolutely not do as a student is incremental research. Incremental research is best done in industry, because incremental research that is done in academia probably won't even transfer to practice, right? Small improvements are too dependent on too many things. And industry has far more researches to improve their existing products with incremental research. The whole point of a PhD, the whole point of academia is to work on really hard problems, because if they're easy, industry will solve them, and also to work on problems with a longer time. Hey, look, if I have a company and there's low-hanging fruit, I'm going to pick the low-hanging fruit first, and that is what I should do. It's my fiduciary duty to pick the low-hanging fruit first. And there are a lot of low-hanging machine learning fruit to be picked out there. There's enormous impact to be had in one industry after another with logistic regression. Don't worry about deep learning until you've done naive Bayes or nearest neighbor. So in academia, however, what we have the privilege to do is work on problems with a longer time horizon, is to do the things that are not going to have a payoff in 3 months, or for which the payoff is very uncertain. And the way to do that is to have a problem that you really care about and then go learn everything that's relevant to that problem. So in particular, if you're interested in machine learning, the question in machine learning is like, how does the system get better with experience? How do I generalize from data? And the single most important thing to remember about machine learning is that we are still in the dark ages. We're at the Galileo stage of machine learning, right? Not, I've heard some people say, like when Mr. Sabe said, like, oh, we've landed on the moon, right? One of my colleagues made this joke on Twitter, like, well, you just climbed up a ladder, right? You don't have a rocket to go to the moon yet. I actually think that's too pessimistic. I think we're at the stage in machine learning where we have propeller planes, which is great. Propeller planes can already fly, right? But they're not the rocket that goes to the moon yet. Here's my prediction. The most important ideas in machine learning have not been discovered yet. It's your job as a student to discover those ideas. And what do you do to discover those ideas? On the one hand, you do have to learn, statistics and optimization and all that good stuff because you don't do machine learning without it, or at least machine learning that really works and is good. But the important ideas in machine learning, they tend not to come from those fields. They come from things like neuroscience, physics, psychology, right? Jitendra said this, and I fully agree with him. We should be all over developmental psychology. There is, the way infants learn is absolutely amazing. Anybody who's a parent can see the amazing things that infants and small children do. We should be drawing on that. At one point, machine learning did draw on that a lot, but this is actually now largely forgotten. If I was a student, what I would do is go study, for example, developmental psychology, bring some of those ideas over into machine learning, combine them with good statistics and good optimization, and that's how you make major breakthroughs. Discover the next great machine learning algorithm.
That's a good. Okay. All right. So I think with that we ended the question that I prepared. But there are lots and lots of questions from Send Online, and I think there are some people on the floor. So now we're going to get a mixture. So let's give some microphone to be used to the people on the floor. And since we don't have voting for the question on the floor, I'll use applause in order to assess whether they get a T-shirt or not. So please applaud vigorously if you think they deserve a T-shirt. And in the meantime, let's just do a quick one from the online part. And again, if you made the question anonymously, just come afterwards and I'll trust you. So this question says, DL is widely used in speech recognition, image recognition, textual analysis, but in other industrial areas such as advertising, video recommendation, and so on, I heard little about it. So is there any successful application in such area? How DL can be used in such areas in addition to feature extraction? So just a very quick things. Can you point out to a very successful application outside speech recognition, image recognition, and textual analysis? I somehow think that Nando might have an opinion on that.
It's available on your phone.
Yeah, I think there are an enormous number of application of deep learning. I think that within Google there are, I think, maybe 1,000 or so in various places. It might not be so visible as the one you see, but certainly all over the place.
I think there are successful applications of deep learning outside of things like vision and speech, but maybe the interesting question to ask is there a distinguishing feature that allows it to predict whether deep learning is going to be good for something or not? And there isn't a perfect one, but there are some ones that are not bad. And I think one clear one is, does the problem have some known structure that you can exploit? ConvNets are successful because images have a 2D structure that they exploit. That's actually what a ConvNet is just exploiting translation invariance. And same thing with speech and language because they're sequential. The places where deep learning has tended to not have a being kept is these places where you're just in a very high dimensional space and you really don't know much about the structure of those variables a priori. So if I just had to give somebody a 30-second advice about whether to use deep learning or not, that's what I would say. If you have a problem that has this kind of structure and you can build a network architecture that exploits it, maybe deep learning is a good solution. Otherwise, probably you want random forests or SVMs or something like that.
Well, how about non-obvious features, right? All of those image recognition, speech recognition, and so on, the features, there are features that are not dominant, and some of them are non-obvious.
Well, they also have this property, right, that the raw variables individually have very little information. This is not the case, for example, in medical diagnosis or whatever, where the raw variables are actually very far from raw. And in traditional statistics, right, you have a carefully assembled data set where the variables are relevant. So deep learning has an advantage where you do have to induce the features. You can't just work with the features that you started with.
I think in terms, also of area of research, this is probably where, a lot of the brain power of young researchers is going to go in the years to come. How to, make the deep learning algorithms work over a wider range of application in domains where learning feature is important but difficult at the moment, basically requires a PhD to go and apply deep learning methods to new areas of application. When is it going to happen that there is going to be a true democratization of deep learning, and people who are not specialists of machine learning can apply deep learning? So we are presently working on automatic machine learning, which is how to put yourself out of business in terms of being a machine learning researcher. And there's much to do in this area, and in order to make it possible that machine learning algorithms will be like cars. When you drive your car, you don't need to be a car mechanic. And so can we have machine learning algorithms that can be used by people in the same way that we drive our cars without having to lift the hood?
Okay, so let's take a question from the floor. I don't know who has the microphone. Okay.
So in the deep learning world, where do you think is going to be the next kind of focus on? Is it going to be on the infrastructure side? In how do you apply, how do you actually implement these deep learning algorithms on large data sets? What is the computing infrastructure that we use? Or is it going to be because of the richness of the new data sets that are being enabled by the different technologies that we need to understand the data and understand the data itself? Understanding the data itself is a big problem. Or is it more discovering new concepts in terms of the algorithms and techniques?
Okay, anyone wants to say where do you expect most progress? And can we pass the microphone maybe to the gentleman in the back that was very...
So at present there's many problems. So like exploration continues being a really hard problem. So if we have agents trying to solve problems where they say delayed reward and so on, we still don't know quite how to come up with good exploration strategies inside of RL systems. And we continue doing that. Good image generation is like one of those things that we're all after. Someone already alluded to being able to understand concepts, program induction, understanding transformations in data, extracting different types of abstractions from data, being able to manipulate those abstractions to solve problems. That continues being a challenge. On the I mean, there's all the scaling problems, energy efficiency. There's the issues of, there's also applied issues, like how do you build good dialogue systems? We already have a lot of dialogue systems that interact with databases to extract information and produce an answer. So there's going to be continued work in that area. Economically, those systems are really important, so there'll be a lot more. So there's really a huge range of really tough problems in deep learning right now. And they're not just like deep learning problems. I mean, they're problems in AI and how to make progress. I see deep learning as become a key component in everything we do with in terms of AI. But of course, there's many other things that we need to keep in mind. As Jitendra mentioned, we need to have a good breadth of techniques. But it's, you know, if you can make progress in any of the things that I just mentioned now, or how to get models that, you know, the thing I mentioned before, get a neural network to spit out the code on how to make generate Python code on how to solve a problem. automatically. I mean, those are good challenges. Currently, those are way beyond what we can do now, but I think they could be achievable within the next 5 to 10 years.
Okay, let's go to the next
Sorry,
question.
can I add one quick thing to that?
Okay, sure.
I think the key problem in deep learning is actually something that has already been brought up. It's learning from unlabeled data. All the top deep learning researchers agree that at the end of the day, we're going to need to be able to learn without labeled data. And if you look at Jeff Hinton, that's actually what he spent 40 years working on. I remember him saying that he hated discriminative learning. He just did it to publish his papers. But the thing is, like, he does care about the right problem. Now the question is, how do we do that? You know, part of that is reinforcement learning, for example, what DeepMind does. Some of these things, like, for example, if you learn from video, it can be self-supervised because you're predicting what happens next, and then you see what happens, and you learn from that. It can be things like vision is supervised by touch. Again, you know, mentioning some psychology experiments, when an animal grows up without being able to touch things, it doesn't understand anything about the visual world. It's just a bunch of ghosts. So there's, I think, a lot of things that can be done that way. Now, if you see what people are doing in the deep learning community, I think some of them are going in this direction. But interestingly, what a lot of people say is, like, we don't know how to solve this problem. So there's definitely a lot of room for new ideas here. Something that you see actually happen in the deep learning community these days is people saying, and I'm going to, you know, cartoonify things a little bit, we've figured out language, we figured out vision. Vision is a solved problem. Speech and language, you know, we're going to get there in the next couple of years. You know, some people have been quoted as saying this. And now where we're going to go next is things like common sense reasoning and planning and problem solving and knowledge representation and, you know, differentiable programming, doing everything with backprop. And, you know, I'm curious to see what comes out of that. I definitely wish them great luck, but I think they don't have a very good idea what they are walking into. Deep learning, so first of all, vision is still very far from solved. Just because you can do good object recognition on ImageNet does not mean that you solved vision at all. So number one, there's a lot more to be done in vision and language. Number two, things like reasoning and problem solving and whatnot, these have been the object of research in classic AI and in symbolic machine learning for decades. People have learned a lot of things there, and what unfortunately you see some of the deep learning folks doing is completely ignoring that and, you know, reinventing the wheel and making it square. You know, that is not the path to success. So I think it'll be interesting to see on that area, but I think there's a lot of combining, you know, the neural learning with other things. Like, for example, you know, AlphaGo is a good example of this. It uses deep learning, it uses reinforcement learning, it uses self-play, which is one of the oldest ideas in machine learning, uses classic AI game tree search. So I think that's the kind of thing that we're going to see more of.
Okay. All right, so let's go to the next question in the back. And remember, please applaud after the question if the question deserves a t-shirt.
Since legislation is being passed in Europe, and Pedro suggested that it's due to misinformation about what deep learning is, what is ACM and SIG-KDD doing to educate legislators? And as a follow-up, you know, what can we do as members of SIG-KDD to make sure that, you know, we educate them better?
That is a great question. And in fact, I think ACM and KDD are doing some of what needs to be done, but they could be doing more. But the thing that we have to realize is that they don't have enough power to do that. I think every one of us, as a member of the community, has the responsibility to try and educate the media, the public, business people, decision makers about these things. These are often things that are completely obvious to us, but that people have no idea about. This is a large part of why I wrote, you know, the book that I wrote, is that at this point, everybody needs to have a basic understanding of machine learning so they don't make some of the mistakes that they're making. And it's the job of every single one of us to try to make that happen. Try to, you know, just tell them, you know, your coworkers, your friends, your family, they need to know about some of these things. And also participate in these debates. You know, speak up. Try to inform people. Don't tell people what they should decide, because it's for them to know what they prefer. But they should know, for example, what a machine learning algorithm is and what it can and what it can't do. And I think it's for all of us to make this happen.
Okay. That's a good question. I will award you a t-shirt. So, okay, so let's do one question from the online community, and then we do a question from the floor. So from June he came. The question is, will the nature continue to be a good source of inspiration for the deep learning researcher? Like, for instance, visual cortex may be inspired convolutional neural network. I think it's a great question. And also, in some sense, many people accuse deep learning of using the term neurons only for marketing purposes because, as Pedro already remarked, neurons are much more connected and in very different ways than actually network layers. So, any comments here?
I can take this. I think there will be lots of ideas which will come from neuroscience and psychology. I mean, obviously, ConNets is a leading example. I mean, the basic architecture is really what was found by Hubel and Wiesel in cat cortex in 1962, for which they got a Nobel Prize in '81. And there was a model of that by Fukushima called the neocognitron back in 1980, preceding backpropagation. And you just add backprop to that and you get ConNets. But we are not going to be slaves to what we know from biology. Obviously, there's a standard example of flight where planes are not built by emulating birds in their gory details of feathers and bones and muscles and so forth. Personally, I think the biggest area of unexploited insights is child development. Child development over the last 30, 40 years, I mean, there is what every parent has some intuitions based on observing their children grow up. But one can study this scientifically, and people have, child development is really a very well studied field where they have good experimental techniques from which they have been able to derive a lot of insights on the process of development. For example, there's a lot which is built into the ability of children. Their ability to learn from single instances, the built-in nature of spatiotemporal continuity, and so on and so forth. The notion of agency. So there is a lot which is there, and a lot which is known today, but a lot of it has not been translated into sort of the language of computer science. It has to be, and eventually we have to test it experimentally, and it has to meet the appropriate engineering tests. You can't have some solution which does not work and just claim that it is worth studying because it was there in your understanding of how humans do it. So I think this is a very promising area for the future. But proceed with caution. A lot of what is stated in the neuroscience and psychology literature, you have to read. You can't just get into it by reading one paper. You have to take this as a serious field which you study.
Anyone else wants to say? Quick. Okay, let's
let me
go to a new question from the floor.
Let me add one quick thing to that.
Sorry?
Let me add one quick thing to that. It's actually, so first of all, I agree that there's a lot to be learned from neuroscience, and some people are actually trying to do that. We know a lot more about the brain now than we did 50 years ago. But you have to notice two things. One is, it takes an enormously long time. So the Hubel and Wiesel work was 50 years ago, and only now are ConVNets taking over the world. The other thing is that the problem with learning from neuroscience is that we don't know any. Everything that we know about neuroscience is infinitesimal compared to what we need to know. In particular, nobody knows how the neocortex learns. The amazing thing about ConVNets is that the neocognitron was actually the architecture of the visual cortex with what Fukushima, with his view of how the cortex learns, but that never really worked. Jan LeCun's idea was, no, let's just apply backprop to this. And the odd thing about backprop is that it's not a plausible algorithm for how the cortex works. It's actually a plausible algorithm for how your cerebellum that does motor control works. So I think we're going to look back on what we have now, 10 or 20 years from now and go like, that was a really weird thing. It was kind of like a Frankenstein monster type of thing. The architecture of the visual cortex with the learning algorithm of the cerebellum. So it actually has to go both ways. We also have to give the neuroscientists some of the concepts that they need to understand how the brain works. In some ways, they need us as much as we need them. And I think it's by the interaction of the two that we're going to make progress.
Okay, so 2 more questions from the floor and we'll be done. So you wanna say something to the current question, or?
Just wanted to add that I'm also a strong believer that we should draw inspiration from biology, and the NIPS conference has been including biology talks from the very beginning. But also let's not lose track of the fact that some of the algorithms that have been very successful are not biologically plausible, including backprops.
Okay, thank you. So, question from the floor. Introduce yourself.
A more mundane question. Many people keep saying large amounts of data. The big problem is finding label data in large. Is it possible, what is large amounts of data first? And is it possible to use deep learning in smaller amounts of data in specific cases?
Okay, this is also a question that many people online have asked.
Okay.
But I think that we somewhat addressed that. Is it possible to do deep learning with much less data,
Well,
or maybe all the way to unsupervised
The
learning?
examples in vision, the standard practice today is that you acquire a basic representation with large amounts of data, like say ImageNet, and then you fine tune it for particular applications for which you need very little labeled data. This is standard practice today.
Yeah, that's part of a larger field called learning to learn. So the idea is you use some data to learn a system that can continue learning and continue solving many other tasks. And there's been a lot of work in that direction recently, showing one-shot concept learning. I think Matt, I forget his name. But anyway, there's been a few papers in this direction. No, but there's psychologist. I should know him because
Josh Tenenbaum.
I just did a Google Hangout with him. But Josh Tenenbaum also pushes this. He's there's a lot of work on how you could learn a neural network, like say a neural Turing machine, and then how once you have that neural Turing machine, there was a paper at ICML that showed that you very quickly do one-shot learning, concept binding. You can learn to do Gaussian process regression, in fact, with a neural Turing machine. They're Turing complete. You can do anything with them. And once you've trained them, they can learn very quickly. There's also a lot of work on one-shot learning, zero-shot learning. So I think, and of course, in terms of unsupervised learning, there's also been a huge progress in terms of variational autoencoders, so the Bayesians can go and work in that area. That's a very exciting area of research in Bayesian statistics, variational autoencoders, so all sorts of models there. Then there's the generative adversarial networks that like keep blowing everyone's mind because they can, with what they can achieve. But it continues being an issue, like especially in reinforcement learning. Low sample complexity is an issue. And here's another challenge. Hierarchical reinforcement learning, or learn hierarchical abstractions, or learn to knowledge that can be reused to solve new problems. Because if you've already learned a lot of things, when you encounter a new problem, by reusing what you've learned, you can solve it more efficiently. We still don't know how to do that.
Okay, let's take one more question.
So this is like a follow-up question on the interpretability thing. My domain is actually in the physical sciences, so some of the pushback I receive from my colleagues is that they don't really understand what the neural network is learning in that sense. And I was wondering, from an applied industrial perspective, is this a deal breaker in terms of adoption of deep learning, maybe a more widespread adoption beyond tech applications like computer vision and speech recognition?
Okay.
I think, unfortunately, this is very common, right? The number one reason why deep learning is not used in an application is that people want explainability and they don't have it. And I think our response to this should actually be twofold. One is we can make deep learning more interpretable and explainable, and we're talking about there are other machine learning methods, like, for example, learning rules that are much more explainable. But I think there's actually a deeper issue here, which cuts to, for example, the skepticism that a lot of physical scientists have about machine learning, which is they say like, oh, I have the laws of physics, what do you have? Right? And the thing about, and it's like, I don't care about accuracy, I care about understanding, right? And I mean, I share that, but here's the thing. Understanding without accuracy is bogus understanding. And number two, right, the laws of physics are an approximation. Everything that we know is an approximation and an oversimplification. And a lot of the people don't appreciate that, but will come to realize in the future is that a lot of the knowledge that machine learning algorithms, with deep learning to the fore acquire, it's real knowledge. Just the fact that we don't understand it is our limitation. In the end, when this is all mature, we're going to have a lot of very rich models of a lot of things, like, for example, models of cell biology that let us cure cancer, and we human beings will not understand those models. But that's not because the models are bad, it's because we are limited. So in the end, the promise of machine learning is precisely to discover things that we human beings don't understand. So we will have to come to accept that and actually take it as a blessing. The fact that we can solve these problems with machine learning.
Jitendra has a slightly different
I want to
opinion.
I don't know if any of you have read this book called Blink. So it's essentially about these judgments, and Kahneman and Tversky have talked about this type 1 thinking fast and thinking slow. So the example in that book is about judging whether a certain sculpture was a fake or not. And the expert sort of knows that it's a fake, but trying to articulate it is much harder. And often, most of our reasoning is, in fact, reasoning is a loaded term here. Most of the processing happening in the brain is subconscious or unconscious. And there is a small part of it which penetrates into our consciousness. So I say to this, hey, let's run a deep network and then train a decision tree on top and use that decision tree to create this illusion of interpretability. Okay? It's going to be not as good as the real thing, which is the neural network, but maybe if it gets your customer happy, what's wrong with it?
By the way, this already exists, right? I know someone who did a PhD, 15 or 20 years ago about extracting decision trees from neural networks to make them more interpretable. And you can do the same thing with model ensembles. So this is a very good thing to have in your pocket if you're in industry and somebody really wants an explanation. I agree with Jitendra. Just give them the illusion of explainability.
Yes, there is actually a...
That's what we do, right? When I'm a doctor and I make a decision and you ask me why, then I make something up, which, will make you happy. But that's not how I really arrived at my decision.
Yes, there is actually a program that writes beer reviews and justifies the scores, and they seem very convincing. And of course, there is absolutely no input except alcohol type of beer and the name.
So there was also a lot of work on extracting finite state automata from recurrent neural networks, which is just along the same lines. And there's been a lot more recent work on trying to understand what recurrent networks are doing by using dimensionality reduction, clustering, and so on. This is a very fertile area. Right now, a lot of people are moving into that, into interpretability and explanation, say like a neural network actually writing in natural language why it reached a particular decision. And I think this is important. We need that illusion, even if it's just an illusion, sort of has to be there. And that when the network provides an explanation, should back it up with evidence. And then at the end of the day, if our minds are big enough that we can understand the explanation, because I think for a lot of things that they're not going to be big enough. I mean, I think a lot of the problems in the world don't come because people are bad or whatever, or politicians are stupid and so on. They just don't have brains big enough to understand how to fix the economy and so on. So at some stage, or how to cure cancer, that's a very important problem that we need to address. So eventually we do need to move beyond decision trees. We need to have complex models that can solve those problems. They might give us some small illusion of explanation, and that's what the European law is about. The European law is about if you get denied a job, you should be given an explanation. You should not just be told you were denied that job because the algorithm says so. And as such, I think it's a very good law, and I don't think England left Europe because of that law.
Okay.
I would like to give a little bit of a complementary point of view here. I think this is a very serious question. Of course, we can, throw a bone to the people who want explainability by training a decision tree and thinking, okay, they ought to be satisfied with that. But there are many applications in which we actually need to do a decision-assisted computer-assisted decision-making, where in fact the human is going to be in the loop, and for very good reasons. We cannot blindly trust the data. The data are not always IID, so the data on which you trained is not necessarily the data on which you're going to be using your learning machine tomorrow. And regulations may change, tiny things may change, and humans are often called to be in the loop, for example, in the medical domain or in many other industry-based applications. I'm at the moment working on an application about power networks, and amazingly enough, in the power distribution network, there are human operators making decisions every 5 minutes about whether to change the architecture of the power network. And they need to be aided by machine learning algorithms, but they're not going to be replaced. And they need to have this kind of explainability. And so how do we do that? That is going to be a tremendous, challenge in research for the next few years. So encouraging people to work in that area.
Okay, I think we are close to running out of time, so I will end it here. I'd like to thank some colleagues that helped me think through the question to ask the panel. Amar Ahmed, I don't know if Amar is here, Sujit Ravi, Sulin Vu, and Alex Mola. And then first and foremost, I should thank the panel. I think we heard a lot of great thoughts.